Yeah, in my last class I was discussing about the limitations of a hard switched converter. I told you that in a hard switch converter the rate of change of current that is flowing through the device or the voltage across the device are uncontrolled. These quantities depend completely on the circuit configuration. I gave the example of a boost converter. The moment you switch the device, whatever the current that was flowing through the inductor starts flowing through the switch. In other words, di by dt through the device is very high. Whereas in a soft switch converter, the rate of change of current and the voltage are controlled using additional L and C. Okay. The size of this L and C is very small. In other words, the resonance frequency of the circuit is very high. So depending upon the power rating, it could be of the order of 500 kilohertz. It could be of the order of 500 kilohertz. So size becomes very small. Okay. Since this voltage rate of change of voltage and current, they are controlled, there is a significant reduction in the device stress. Okay. There is a significant reduction in the switching losses. So I will just give an example here. So this is the slide. Okay. There is a current flowing through the device, voltage is falling here. Okay. See, this is if I plot in the same graph, intersection takes place at this point, voltage across the device is relatively high, it has not attained its saturation voltage. Okay. Current has risen to a significant value. Okay. So instantaneous power loss that is taking place in the device is quite high. Okay. So the device loss during the switching is high, stress is also high, di by dt C is very fast, very high. Okay. Whereas in a soft switch converter, see, the voltage has become 0. How we will see? I said we need to use a separate L and C. Okay. Voltage across the device has become 0 and then slowly current starts rising. Okay. So voltage across has attained its saturation value, current starts rising. In other words, the switching losses are practically eliminated. And see, this current rise is a LC circuit, some sort of a resonant current. So there is a significant reduction in the di by dt also here. Okay. You compare these two. This happens both ways. Okay. While turn on as well as while turn off. So let me repeat, in a soft switch converter, there is a significant reduction in the device stress, there is a significant reduction in the switching losses. Since there is a reduction in the switching losses, now there is an improvement in the inverter efficiency. Losses are reduced, therefore operating temperature comes down, the cooling requirement reduces. Now there is di by dt is controlled. In other words, there is a reduction in the EMI, electromagnetic interference. Okay. Another very important advantage of short switch converter is that it is possible to increase the switching frequency. Okay. Now you can operate the converter at a very high switching frequency. In a hard switch converter, because switching losses are high, you have to reduce the switching frequency, even though the device may be able to operate at a higher frequency. In other words, you will not be exploit all the good qualities of a device because of hard switching. Okay. There are two types of soft switch converter. What are they? One is zero current switching, and another one is zero voltage switching. Okay. See, before showing this figure, I will just show you, explain this graph. I had explained to you in my previous lecture. See, the voltage across the device has fallen to a very low value, it is relatively low, and only then current starts increasing, only then the current starts increasing, and vice versa. Current decreases, it is a relatively low value, and then voltage across the device increases. So this is the area, this area is nothing but the losses, whereas in a hard switch converter, see the locus. Current increases, reach a fairly high value, voltage has not reduced and comes down. And this is all because of the parasitic elements, and this is while turning it off. Now I had also told that the losses that are taking place in the device can be reduced by using a external snubber. Okay. A passive snubber, if I use, losses, the switching losses can be reduced. At the time, this is the locus. There is some controllability. In other words, both dV by dt and di by dt are controlled. But then these losses that are taking place in the device, they are transferred to the external circuit and they are dissipated there. Okay. See, the zero current switch converter and a zero voltage switch converter, basic topology, simple topology. There are various circuit configuration. One such example I have given here, say zero current. Why am I calling this zero current? Assume that switch is open, no current in this branch. Okay, I will close the switch. Because of this inductor, current through the switch cannot change instantaneously. It has to start from 0, okay, slowly rises, slowly increases because of this inductor. Hence the name zero current switched converter. I will repeat. I will close the switch, current at t is equal to 0 minus, or just prior to closing the switch it is 0. I close it, still the current is 0 because of this inductor, and now current starts increasing slowly. Okay. Come here in the zero voltage, just see, I have connected a small capacitor, a very small capacitor. Okay. We know that voltage across the capacitor cannot change instantaneously. Okay. So assume that switch was closed. Okay. So voltage across it is approximately 0, or its saturation voltage. Now I will open the switch. Okay. Since I have connected a capacitor, voltage across it cannot increase instantaneously. It will slowly rise. it will slowly increase, slowly increase. In other words, voltage across the device starts from 0 and slowly it will increase. Yeah, hence the name zero voltage switched converter. Okay, so basic topologies, one of the topologies. So using separate L and C, so now it is possible to reduce the switching losses, it is possible to reduce the device stress. What do I need to do this? The existing power electronic converter now should have additional L and C circuits, that is all. Okay. Size of this L and C is really very small. Okay. So what are the, if I have to summarize, what are the advantages? The advantages are here. Device stress reduces. Okay. There is a significant reduction in electromagnetic interference. Remember, if you have to sell your product in the international market, for that matter even in India, we have our own, or India, there is IS standard. Okay. So to sell the product in the market, you have to adhere to those standards. Okay. So if the EMI is very high, you will not be able to sell it in the market. Okay. So there is a significant reduction in EMI. Switching losses are practically eliminated. Okay. I said they require separate L and C. Now this L and C could be the parasitic elements itself. Parasitic element itself. See, these parasitic elements created an additional spike in the current or voltage during hard switching. I showed you the locus of voltage and current. Either there is a spike in the current or there is a spike in the voltage. That is because of the parasitic elements, parasitic L and C. Now now it is possible to use these parasitic elements for our advantage. Okay. And last one is, it is possible to improve the diode recovery, or in other words, it is possible to switch the diode under zero voltage or zero current situation. It is possible. You have to modify the circuit. Okay. By the way, I have been talking about the advantages of the soft switch converter. Definitely there has to be some disadvantages. What are they? They are very obvious. Circuit operation now is a bit complex. Circuit operation is slightly complex. Okay. Second, the peak current is higher. Peak current is higher. Okay. See, I'll show you. See here. After all, power transferred is a product of V and I. Okay. See, current is approximately remains constant here, whereas it starts from 0, slowly rises. Okay. And it is a sinusoid. So area should be the same. Okay, for the same power maybe. So therefore definitely the peak current should be higher. Okay. So in other words, peak current through the device has increased. Peak current through the device has increased. Where is the major application of this soft switch converters? The major application, one of the major application is in power supplies. Power supplies. If you have to reduce the size, if you have to reduce the weight, you have to increase the switching frequency, and it is possible only using soft switching technique. It is possible only using soft switching technique. So soft switch DC to DC converters are very popular, very popular. So this doesn't mean that soft switching is not used in AC to DC converter and maybe DC to AC converter. I have not covered DC to AC so far, but the major application or major use of short switching technique is in DC to DC conversion. Okay. And second one is in induction heating. Induction heating, we require a high frequency AC source. High frequency AC source. Higher the frequency, the better it is. Okay. Maybe sometime later I'll explain to you the requirements of induction heating. Okay. You require really a high frequency AC source. There also soft switching technique are used. Soft switching techniques are used. Another is the lighting ballast choke. A power efficient small electronic ballast. Power factor also unity there. A soft switched or a resonant technique even is used in electronic ballast. Okay. So these are the major applications. I will not discuss much on soft switch converters because let me tell you one thing, this is a subject by itself, it's really vast. I just introduced the concept of zero switching to you. Okay. With this, I have completed, in fact I should not be using the word completed, I will stop discussing DC to DC conversion. Okay. We did discuss 4 different types of topologies without using a transformer. They are buck converter, boost, buck boost and choke converters. Then we started discussing the topologies using a transformer. They are flyback, forward and push pull. Then I introduced little bit of the concept of soft switch converters. With this, I will stop the DC to DC conversion topic. Now I will start discussing another important area in power electronics, that is DC to AC conversion. Okay, DC to AC conversion. These are also known as inverters. Okay. Now let me clarify one point. Recall our discussion in AC to DC conversion. Okay. I said that AC to DC conversion or AC to DC converters, also known as converters. In a fully controlled bridge, if alpha is equal to greater than 90, I told that it is known as inverter. Okay. Now again here I am saying if the input is DC and output is AC, they are known as inverters. Yes, both are known as inverters. But then the first group, or when the input is AC, output is DC and alpha is greater than 90, and if the load is active, power is being fed back to the source, this equipment is known as line commutated inverter. Line commutated inverter. Okay. So therefore, if someone says inverter, by default you can take it for granted that input is DC, output is AC. Okay. Now don't please confuse with the line commutated inverter and DC to AC converter. No. Okay. By the way, why is there a need for DC to AC converter? I told you AC to DC conversion, yes, we require, because to control the speed of a DC machine. DC to DC conversion may be required in power supplies. Now why DC to AC? See, the voltage or the power that is generated in the generating station is alternating, except for solar power or power that is obtained from solar cells. Almost all the power is alternating, AC power, because if I rotate a conductor in a magnetic field, whether the magnetic field is AC or DC does not matter, the voltage induced in that conductor is AC. Okay. So power that is generated is AC. Now I am going to discuss a equipment which converts from DC to AC. Why you require this? Why is there a need for this set of equipment? And why did I say is another very important area in power electronics? So let me tell you one thing. If there is a equipment which converts DC to AC, that equipment should also have a AC to DC converter. Okay, it's like this. See, I'll first convert AC to DC, because power that is generated or power that is available is AC, except for solar, the DC, and from this DC to AC. Okay. But then in this topic we will discuss, will concentrate only on DC to AC. Okay. How to get this DC we have already studied, okay, in AC to DC conversion. Now I will give you two examples, two applications. Take for example the inverter which is used in our home, or a UPS is used in a computer center as a backup. What the inverter which is used in a home does? The moment the utility power supply goes, or the moment there is a power shutdown, that inverter converts whatever that energy that is stored in the battery, it could be either 12 volts or 24 volts, to 230 volts 50 hertz AC. Okay. So the inverter converts 12 volt DC to 230 volt AC. So during normal operation, or when there is a utility supply available, the battery is getting charged. So there has to be a small bridge which converts AC to DC and charges the battery. Okay. If the battery is discharged, it charges, and afterwards it is floating in the DC bus. So that is the reason I said, if any equipment which converts DC to AC should have a AC to DC converter. So one of the application is 12 volt DC is the input and output is 230 volts 50 hertz AC. Over here I have drawn a sinusoid. Whether it is a sinusoid or how to get the sinusoid we will see sometime later. So one of the applications is output should be constant voltage and constant frequency. Okay. Remember, from a DC output should be a constant 230 volts and a constant 50 hertz supply is required. Okay. Now I'll just take a small diversion, go back to AC machine theory. Please, for half an hour or so I'll discuss the principle of operation of induction machine. Okay, you might have already studied this in your machines course. So let me briefly revise this. So we all know that when a 3-phase sinusoidally distributed winding which is excited by a 3-phase currents, the stator field is rotating. In other words, when you connect a 3-phase stator to a 3-phase AC supply, the field produced by the stator is rotating at synchronous speed, and that synchronous speed is 120 f by p, where f is the supply frequency. Initially, rotor is stationary, nr is equal to 0, stator field is rotating at ns, so ns minus nr is nothing but the relative speed between the stator field and the rotor is ns itself, because rotor is stationary. Since the relative speed is maximum, a large current will flow in the rotor. This current has to come from the stator, so there will be an equivalent current flowing in the stator. This current, the stator current, has to come back or has to come from the source. So in other words, when you switch on the 3-phase induction machine to the source, a large current will flow, and this current could be of the order of 6 times the rated current. Okay, it could be of the order of 6 times the rated current. Okay, I am emphasizing this because we need this when we are discussing in detail about the inverter operation. Okay. So current carrying conductor placed in a magnetic field experiences a force, this all we know. So stator has established a field, there is current flowing in the rotor conductor, so therefore rotor starts accelerating. So nr increases, as nr increases, ns minus nr decreases, in other words relative speed falls. If the relative speed falls, current in the conductor also falls. Rotor starts accelerating and it will attain a steady speed which is less than the synchronous speed. Okay, and at that speed the torque produced by the motor is equal to the load torque. Okay, so here is the speed torque characteristics of an induction machine, which I already studied in a machines course. Okay, now assume that a constant load is being applied to the shaft. In other words, the rotor is driving a load whose torque is independent of the speed. See here, I represent that characteristic by a straight line. Load torque remains the same. Okay. Since load torque has remained the same, the electromagnetic torque is also will remain constant, and it is independent of the speed. Okay. So what is electromagnetic torque or developed torque? Is nothing but air gap power input P2 divided by 2 pi ns. So this is the expression, a very popular expression, P2 divided by 2 pi ns. This is nothing but the developed torque, where P2 is the air gap power input. Now Ns is constant because our Ns depends only on the frequency of the stator supply. Therefore, if Ns is held constant, okay, and the machine is driving a constant torque load, okay, TL remains constant, P2 or the air gap power input remains constant. Okay. Now this air gap power input is approximately equal to the input power itself. Okay. So therefore, what I can conclude is that the input power is almost independent of the speed if the machine is driving a constant torque load. I will repeat, the input power to the machine is almost independent of the speed of rotation, provided the machine is driving a constant torque load. Okay. So what happens if you want to reduce the speed of rotation? I am saying frequency is held constant. Okay. So if you are trying to reduce the speed of rotation by reducing the applied voltage, okay, I will keep frequency constant. I am just trying to reduce the applied voltage, maybe using an auto transformer also. That is what we have done in our machines course or machines lab. Okay. Since synchronous speed is held constant, the input will remain constant. Speed of rotation has come down, assuming that speed of rotation has reduced, the slip has increased. Slip has increased. Ns minus Nr divided by Ns. Nr has reduced, Ns is constant, slip has increased. If slip has increased, S times the air gap power input is dissipated as heat in the rotor copper losses. Okay. So there is an increase in the rotor copper loss. If there is an increase in rotor copper loss, the temperature rise increases. Okay. Since there is an increase in the rotor current, and I told you this current has to come from the stator, there is an increase in the stator copper loss also. In other words, there is a reduction in the efficiency of the motor. Okay. See in this plot, a torque speed characteristics for one supply voltage V1. I will try to reduce the stator applied voltage to V2. All these points will remain the same. Peak torque or speed at which the peak torque occurs will remain the same. The synchronous speed also will remain the same. Okay. The intersection of the load characteristics with the motor characteristics is the operating point. Okay. Now if I expand this region, see it looks like this. I have expanded, I exaggerated. Initially it is operating at NR1, okay. When I tried to reduce the voltage, it started operating at NR2. Ns is constant here, synchronous speed. Now the machine is operating at NR2, so there is an increase in the slip compared to the previous case. Okay. So there is an increase in the slip, P2 is constant and it is independent of the speed of rotation. That's what you have proved. So S times P2 is dissipated as heat. Okay. Now, what is the relationship between electromagnetic torque and the slip? See here, P2 is nothing but I square R by S. So this is what we have studied again in the machines class. So that is nothing but TE. Okay. So what is the relationship between this I and S? I is proportional to square root of S. I is proportional to square root of S. Okay. So as S increases, stator current also increases, and therefore stator copper loss increases. Okay. So there is an increase in the stator copper loss, there is an increase in the rotor copper loss, therefore there is an increase in the heat developed, and there is a reduction in efficiency. Okay. Now take for example the second case, a very popular type of load, a fan type of load or a pump. What are the characteristics? Load characteristics of a fan? TL is proportional to the square of the speed. TL is proportional to the square of the speed, that is NR. TL is proportional to NR square. So what is NR? 1 minus S into NS. So therefore TL is proportional to 1 minus S square. Just now I showed you that T is proportional to I square R by S. This is nothing but air gap power input, Okay. So T is proportional to I square R by S. So at steady state, and if I neglect the frictional and windage losses, these two should be equal. IR squared by S should be equal to, or should be proportional to 1 minus S square. So therefore what is the relationship? I is equal to, or I is proportional to this. Okay. Now if I plot the magnitude of I versus the slip, I will get this sort of a characteristics. Okay. You will find that current is maximum at S is equal to 1 by 3. Okay. It is very simple. You need to differentiate this equation with respect to S and equate it to 0. 1 minus S into square root of S, you differentiate it with respect to S and equate it to 0. You will find that at S is equal to 0.333, I is maximum. Whereas if the torque remains constant, I is proportional to square root of S. Okay. Which is not the case if the load is of fan type. So please remember, okay, characteristics or the operation changes and it depends on the nature of load. Machine may be the same. Okay. So what do we conclude? We can conclude that if the process requires wide variation in speed, NS should be changed, especially for constant torque applications. Okay. If the process requires wide variation in speed, synchronous speed should be changed. Okay, especially for load torque remains constant. And please remember, in principle this may not be required. In other words, you don't need to operate this, you don't need to change the synchronous speed for fan type of loads, in principle. Why? It's because in constant torque type of load, the input power is independent of the speed of rotation. That's what I told you in the beginning. If the load torque remains constant, input power will remain constant and it is independent of speed of rotation. Whereas if the load torque depends on the speed, and for a fan type of load torque varies with the square of the speed. So as the speed of rotation decreases or changes, input also changes. Okay. So here is it. Stator current attains a peak at S is equal to 1,3 and again it comes down. Again it comes down. Please, it attains a peak at 1/3 and it comes down. Okay. So in principle, you can vary the speed of a fan type of load by varying the applied voltage to the motor, keeping the frequency of the stator supply constant in principle. But then for a high power fan, say especially in a power plant, in a cooling tower, the rating of the fan could be a fraction of a megawatt. It could be of 1.2 megawatt or so. It's that high. Cooling tower fans, or if you have a pump, a boiler feed pump, say HP rating could be of the order of 2000 or so. Say 235 megawatt power plant, the boiler feed pump kilowatt rating could be of the order of 2000 or so. Okay, and cooling tower fan could be of the order of 1.2 megawatt or so. Okay, so there, if you want to vary the speed over a wide range, in case if you want to vary the speed over a wide range, or if you want to vary the discharge over a wide range, it is preferred to vary the synchronous speed. Okay. So therefore, if you want to vary the speed of rotation of an induction machine, and if you want to maintain a very good efficiency, what do we need to do? You have to change the frequency of the stator supply. Okay. So I will repeat, for a wide variation in speed of an induction machine, stator frequency has to be varied. So far I have not told you the relationship between the stator frequency and the magnitude of voltage that is applied to the induction machine. I just concluded that to vary the speed over a wide range, you change the frequency of the stator supply. What should happen to the magnitude of voltage? Okay, we will see. Again, I will go back to induction machine theory. See, here is the equivalent circuit, a very popular equivalent circuit. Stator parameters, rotor parameters, equivalent load, magnetizing inductance. Okay. And what is torque? We all know, very popular torque expression. Torque is proportional to Fs, Fr, sine of the angle between Fs and Fr, or torque is proportional to FSR and Fs, sine of the angle between FSR and Fs. And the third expression is torque is proportional to FSR and Fr, sine of the angle between FSR and Fr. These might have studied again in the machine score, basic equations. So if I use the same expressions here, one of them, FSR is nothing but the air gap flux phi. FSR is the resultant magnetic field, that is nothing but the air gap flux here phi. Fr is the rotor MMF, that is nothing but, or it is proportional to IR prime, current that is flowing in the rotor circuit. Okay. Now this flux phi is produced by the current that is flowing in the magnetizing branch, Okay. So therefore phi is proportional to Im. Okay. Now what is Im? Im is given by E1 divided by 2 pi f into Lm, 2 pi phi into Lm. Okay. Generally, if the HP rating of the motor is high or high power machines, stator resistance is very small. Stator resistance is very small. In other words, so this is the equivalent circuit. All the series elements, all these elements should be as small as possible, because this is the main path of the power flow. Power flows in this direction. Okay. So this should be as small as possible. Okay. This should be as small as possible. For invariably they are for a high HP machines, which may not be true for a low HP or fractional HP machines. Okay. For a high HP machines, these parameters are very small. If these parameters are very small and at relatively high frequency in the sense maybe of the order of 25 to 50 hertz, okay, these are approximately I have drawn, please. Okay, so from 25 to 50 hertz, also I am calling this as high frequency, I can say that magnitude of E1 is approximately equal to Vs. See, while doing, I will recall the transformer equivalent circuit, transformer approximate equivalent circuit. What did we do? We shifted that magnetizing branch and connected across the supply, and we called that circuit as an approximate equivalent circuit. Okay. Same thing I am doing. Okay. I am shifting that magnetizing branch to the supply, and this circuit is, and I am saying that this is valid at relatively at high frequency. So fortunately we concentrated or we used a 50 hertz supply rated frequency. So there the change of frequency did not arise. Here, before coming to this topic, I concluded that stator frequency should be changed or should be varied in order to vary the stator frequency, in order to vary the speed of rotation. So I am shifting this branch to the input, and I am saying that V1 is approximately equal to Vs, and this assumption is valid only at relatively at high frequency. Why? I will tell you sometime later. So at relatively at high frequency, V1 is approximately equal to Vs. See, I have just drawn a vector diagram just to tell you. Maybe this is a bit exaggerated again. I am taking E1 as reference. Okay. And some Is lagging current, because current has to be lagging in induction machine, ISRS, Is into XSL, this is Vs. So the magnitude of V1 could be approximately equal to magnitude of Vs, because these parameters are again very small for air. So therefore Im is equal to Vs divided by 2 pi f into Lm. Okay. Im is equal to the supply magnitude of the supply voltage divided by 2 pi f into Lm. Now we will discuss various cases. Case 1, I will keep Vs constant and I will try to reduce the frequency, okay, because I have to reduce the speed of rotation. So frequency should be reduced. So what happens? See, in this equation, I will keep Vs constant and try to reduce the frequency. So this equation says that Im tries to increase, Im increases, in an actual machine whether it increases or not, we will see later. Okay, Im increases. If Im increases, flux increases. Okay, I told you that, or it is known that machines, or the magnetic circuit that is used in the machines or in transformer always operated at the knee point. The magnetic circuit is generally operated at the knee point. Okay, a knee point is a point wherein the saturation begins to start. Okay, till the knee point magnetic circuit is linear, and above the knee point it starts saturating. Okay, it is going to be non-linear. In this equation I am keeping V as constant, trying to reduce F. Im increases, therefore flux tries to increase. If flux tries to increase, magnetic circuit starts getting saturated, and if the circuit saturates, the source current is going to be peaky. Okay, source current becomes peaky, harmonic content increases, plus core loss increases. Okay, so therefore keeping Vs constant, or keeping the magnitude of voltage constant and decreasing the frequency in order to decrease the speed of rotation is not a solution. Okay, I will repeat, keeping the magnitude of voltage constant and trying to reduce the frequency in order to reduce the speed of rotation is not a possible solution, because machine will get saturated. Okay, the remaining cases we will see in the next class. Thank you.